Hello everyone, this video covers section 4.3. For the rest of the chapter, we're gonna focus only on integration. Only section 4.1 and 4.2 were about differentiation. And the basic idea of integration is something that you technically already saw in calculus. So remember, if you have a function that looks like this and you wanted to find the area from here to here, from A to B, the most basic approach of what we did before is you can create technically rectangles, okay, or quadratures. So you can see the area of these two rectangles is not the same, but it's close. And the more you do, the closer the approximation will be. The key point throughout the whole chapter, not just 4.1, is, well, how are we going to create these rectangles or these quadratures? That's the fancy name, quadratures, so that we can have a more accurate result. In calculus 1, remember you let the length or the base go to 0, and then we call this the Riemann sums. But just like a numerical differentiation, we cannot really go to infinity or to 0, or as n goes to infinity. So that's we had to come up with different methods to find the best possible area or integral. Now recall, just like what we did for numerical differentiation, the f of x can be written like this in terms of Lagrange polynomials, where this is the error. So in section 4.1 we take the derivative, so now we integrate. So in theory this will be the approximation to the integral, where this will be the truncation error. Now, just for notational purposes, notice that this can be written this way. So this is the product from I equals to 0 to n of x minus x I. So this, and this is the exact same thing. Now, since these are rectangles, remember, to find the area of a rectangle, you need the base and you need the height, okay? So here the height is going to be the value of the function. So this technically will be the height, which, remember, this is a constant, so you can take it out. And therefore, if you integrate, this will give you the following. This will be the sum from I equals to 0 to n of ai of f of xi, okay? Plus, and all of this will be the error function, like I mentioned it a few minutes ago. So therefore, your job technically is going to be able to figure out the values for ai, which will be the integral of the Lagrange the Lagrange polynomials from I equals to 0, 1, all the way to n. All right, so let's start with the most basic method, which is the trapezoid rule. For the trapezoid rule, the value for n is equals to 1. So therefore, h, which is b minus a over n, in general, is just going to be b minus a, where the function you're trying to integrate could look like this. And you're integrating from a to, let's say, b. And here x0 will be a and x1 will be b. So therefore, from here, this implies that h in this particular case is just x1 minus x0. Okay, just remember that. The reason why this is called trapezoid is because if you have these 2 points and you make a straight line through there, and then we find this area, you can see you find the area of a trapezoid. And technically it's just one of them. And this is the most basic method. So all you have to do is find this area, and that will be the approximation to the integral. So now we're going to do the fancy derivation of the trapezoid rule, which is actually pretty straightforward. It just looks messy because of the notation, but it's pretty simple. Now, just for notational purposes, so we can keep the notation clear, this part is technically what we call Pn before, okay? So this is Pn. So if n is 1, then we will have the trapezoid case, which is what we're going to do right now. So that's why we're finding P1. So therefore here the sum is just from 0 to 1, and that's why you end up with two terms only, which is this one and this one. So we'll go 0 and 1. Okay, so this is exactly the same thing. All right, so now let's derive the trapezoid rule in the fanciest possible way. So here it is. So we're trying to find or to approximate the integral of f of x. The x, well, remember in our case, a is equals to x0 and b is equals to x1. And then we just pretty much write this in here. So this will be, we're trying to integrate x minus x1 over x0 minus x1 times f of x0 plus x minus x0 over x1 minus x0, the whole thing times f of x1, and we're integrating with respect to x. Here you just have to be careful what is actually a function of x and what is a constant. And then we have the error function, which that will be equals to 1/2. The reason why is 1/2 is because the value for n is 1, so n plus 1 is 2, 2 factorial is 2. So it will be 1/2 the integral from x0 to x1 of the second derivative evaluated as some c of that depends on x times x minus x0 times x minus x1, since you only have two points. And remember, this is what we're going to call EF, or the error of the function f. Now the computation part is going to be this. So let me just call this T for now, because that's going to be the trapezoid, and that's going to be the actual computation part or approximation. All right, so therefore T is going to be the integral with respect to x of this. So if we integrate, we'll end up with 1/2, and this will be x minus x1 squared divided by x0 minus x1 times f of x0. Because remember, these are constant and these are constant with respect to x. And then plus 1/2, and then x minus x0 squared over x1 minus x0 times f of x1. So that's the integral, and the limits of integration are from x0 to x1. Notice that when you plug in x1, this part will be 0, but this won't be 0. And when you plug in x0, this part will be 0, but this 1. So once you plug the limits of integration and do a little bit of algebra, you'll end up with the following. This will give you 1/2, and then x1 minus x0 squared divided by x1 minus x0 times f of x0 plus f of x1. And then this simplifies to just x1 minus x0 divided by 2 times f of x0 plus f of x1. But remember the x0, or x1 minus x0 is equals to h. So therefore this is just equals to h over 2 times f of x0 times f of x1, which is the most basic method to approximate an integral, and therefore you should not expect it to be very accurate. Okay, now let's look to the error formula. So the error formula of the function f, remember, is equals to 1/2 the integral from x0 to x1 of the second derivative evaluated as one can see times x minus x0 times x minus x1, the whole thing dx. Okay, now since, and this is going to be very useful in many of the proofs you do later, since x0 times xx and x minus x1 times x minus x1 doesn't change sign in the interval x0 to x1, therefore by the weighted mean value theorem from chapter 1, so this is the mean value theorem for integrals. You can just take out the derivative, so this will be 1/2 the second derivative for some c times the integral from x0 to x1 of x minus x0 times x minus x1 dx. Now, if you expand and integrate this, you should definitely stop this and check your integration skills. This is the same thing as x cubed over 3 minus, and then this is going to be x1 plus x0 over 2x squared, and then plus x0 times x1 times x. Again, just stop the video, and this is a good way to practice your calculus 1 skills. Once you plug in everything, which is a little messy, and simplify, so you're going to end up with this. The second derivative evaluated at c over 2, and then this will be x1 cubed over 3 minus x1 cubed over 2, and then x0 times x1, this one is a square divided by 2, then minus x0 cubed over 3 when you plug in the lower limit, so you will end up with this. So this is some very tedious algebra, but that's the only way to check that we'll get what we're going to get right now. So once you simplify all of this, you will end up with a second derivative at c divided by 2 times negative 1/6, which is the LCD, and then it will be x1 minus x0 cubed. But remember that x1 minus x0 was equals to h. So therefore this is negative 1/6 h cubed when you simplify. The second derivative evaluated as 1 can c divided by 2. And this will be the error formula. So this is what E of f will be. And this right here is the one that you're going to use for computation or approximation. So let's see how this works. All right, so here we want to approximate the integral of 1 over 1 plus x squared. And here the value for, let's say we want to integrate this from 0 to 1, which the question doesn't tell you that, but it has to tell you that. So therefore, you want to approximate the integral from 0 to 1 of 1 over 1 plus x squared dx. Here, notice that the value for n is, remember, 1. That hasn't changed. So therefore, h is going to be equals to 1 minus 0 divided by 1, which is just 1. And here x0 is equals to 0 and x1 is equals to 1. Okay? So therefore the approximation, so the integral of 1 over 1 plus x squared dx is going to be around 1/2 f of 0 plus f of 1. As you can see, it's very, very simple. So this is 1/2. And then this is 1 over 1 plus 0 plus 1 over 1 plus 1. And this is equals to just 0.75. Okay. Now, let's compare that with the exact solution. Remember, the integral from 0 to 1 of the x over 1 plus x squared is just tangent inverse of x from 0 to 1, which is equals to tangent inverse of 1 minus tangent inverse of 0. This part is 0. And this is just pi over 4, which is around 0.785398. So as you can see, for this particular case, this is not that bad. And the reason is that the graph of 1 over x squared looks like this. So when you do a trapezoid, it's going to be very close from 0 to 1, which is this part. Now, if you use 2 points, which means now we're going to use P2, and this is the representation of P2 using the Lagrange polynomials, then we're going to get the method that is called Simpson's rule. And Simpson's rule uses now 3 points, x0, x1, and x2. So in this case, you technically have two rectangles, and you're going to find the area of those two, and that's going to give you the approximation, and this will be the error term. Now, if you do what I did in the previous example, using integrating all of this beautiful thing, you should end up with exactly this, and I believe that's a homework problem. Also, if you do exactly what I did in the previous one, and you integrate the error form, you should end up with something like this. And even if it's not a homework problem, you should check yourselves that if you integrate this, it should give you this, and that the error formula will give you this. That's going to be very important, especially for the exams. All right, so here for Simpson's rule, since it uses 3 points instead of 2, so now the value for h is going to be now x1 minus x0, which is technically b minus a, divided by 2, because now the value for n is 2. So therefore, we're going to have just x1 minus x0 over 2. That's going to be the value for h. All right, so let's do the exact same example we did right now. But now we're going to use this method instead of the trapezoid and compare the results. Okay, so now remember that we're going from 0 to 1. And you divide this by 2, therefore this will be 1/2. So therefore this is equals to x0, this will be x1, and this will be x2. And the value for h is going to be 1 minus 0 over 2, which is 0.5 or 1/2. Right, so therefore the integral from 0 to 1, if we use the Simpson's rule, is going to be approximately equals to 1/2, which is h divided by 3. So we're just following the formula. And then this will be f of 0 plus f of 1/2 times 4 plus f of 1. And this equals to 1/6 times 1 plus 4 times 1 over 1 plus 4, because 1/2 squared is 4, 1/4, and this will be 1 over 1 plus 1, and when you simplify everything, this is 0.7833, which you can see is closer to the exact solution than the 75. So as you can see, the actual computation or approximation is very, very simple to do because the formulas are straightforward. The hard part here is going to be to come up with the formulas or to calculate the error or get the actual error formulas. That's the tricky part. Now there is a concept here that we're going to use throughout the rest of chapter 4.2. There's something called precision, and people usually have a hard time with this at the beginning, so this is what it means. The definition is not very friendly, but once I do a few examples, hopefully it will make sense. So the degree or accuracy or precision of a quadrature formula, remember all of this is a quadrature formula. The trapezoid is a quadrature formula too, and technically we'll have many of them, is the largest positive integer n such that the formula, which will be this, or the trapezoid, is exact for x to the k. That means that if you integrate this function over here, this is referring to f of x equals to x to the k, and if this gives you the exact same integral by doing a regular integral or doing the method, then the highest value of k, that will be the precision of this method, meaning that there is no difference between the actual integral or doing the method. For example, let's start with the most basic example again, which is the trapezoid. So you look to the trapezoid. All right, so the exact solution, we're always going to start with the most also basic polynomial, which is 1. Remember, x to the 0 is 1, x to the 1 is x squared is x squared, and so forth. So you always start with the most basic one, and that will be precision 0. So if you integrate from a to b of just 1 dx, the integral of this is clearly just b minus a. And if we look to the method, the trapezoid method, if we're going to integrate 0 to a, from a to b, sorry, of 1 dx, this will be b minus a, which is x0 minus x1, or x1 minus x0, divided by 2 times f of a plus f of b. But remember, for this particular case, f of x is equals to 1. So therefore, this will be b minus a over 2 times 1 plus 1, which is also 2. So this cancel, and this is just equals to b minus a. So at the very least, the trapezoid has precision 0, which if you don't have precision 0, that's a pretty bad sign. So this and this are the same. So at the very least, it has precision 0, because this is the case where f of x is equals to 1. All right, so then if that works, then you move to f of x equals to x, then x squared and x cubed and so forth until it doesn't work. So for x, the exact solution will be the integral from a to b of x dx. This is x squared over 2 from a to b. So this gives you b squared minus a squared over 2. All right, so now if we use the trapezoid method, the integral from a to b of just x, d of x, using the trapezoid method is going to be b minus a over 2, which is just h over 2. And then this will be f of a plus f of b. But f of x here is equals to just x. So therefore this will be b minus a over 2 times b plus a. But remember that b plus a times b minus a is the same thing as b squared minus a squared. You distribute, and you can see that this is exactly the same thing as this. So now, at the very least, the trapezoid has precision 1. All right, so now let's check f of x equals to x squared. So the exact solution from a to b of x squared dx is equals to x cubed over 3. And then if you plug the limits of integration, this is equals to 1/3 b cubed minus a cubed. However, you do the method, so now the integral from a to b of x cubed sorry, x squared dx, this is still going to be v minus a here over 2, but now this is going to be b squared plus a squared. And notice that this is not equals to bq minus aq over 3. So therefore the maximum precision you have is 1. So therefore the trapezoid, this one has precision 1. Again, you're going to see this multiple times throughout chapter 4. And you should check the Simpson's rule, which is the one we just did too, has precision 3, or n equals to 3. All right, so you should give it a try and check this works. So what this means by being precision 3, it means the Simpson's rule, you, let's say, find the integral from 0 or from a to b of x cubed dx, which this will be x to the 4 over 4 from a to b, or b to the 4 minus a to the 4 over 4. When you do the Simpson's method, when you integrate this from a to b of x cubed dx, it should give you exactly this function again. So you should check it out. But you should start with n equals to 0, which is this, then 1, then 2, and so forth. Again, you're going to see these questions multiple times throughout all of chapter 4. Now, before we go to the next page, the trapezoid and the Simpson's rule are special cases of something that is called Newton codes. You can have either closed Newton codes or open Newton codes, like you will see in a little bit. So instead of using just 1 point, or 2 points in the case of trapezoid and 3 points in the case of Simpson, you can have 4, 5, and so forth, and they are called Newton codes. So let's see what that means. So first, let's look to the closed Newton codes. So closed means this, that you start in A and you go to B, and you're only gonna use the information from here. You will not use anything outside. So then you cut the interval into n pieces. So you're gonna have n plus 1 points, and you are gonna evaluate it at n plus 1 points. Okay, then you're gonna have to come up with a method, but it's gonna be the same idea. So suppose this denotes the n plus 1 point closed Newton codes formula. So again, closed means you cannot use any points here or any points there, where x0 will be the star and x being will be the n. Okay, so then there exists a c between a and b, which will be somewhere in here, for which the integral will be approximated by this, which we did already this for n equals to 1 and n equals to 2, and this will be the error term. Again, so we already looked to this method, trapezoidal. So remember here n equals to 1, and the value for h here was just x1 minus x0 divided by 1, so therefore it's just x1 minus x0. We also look to Simpson's rule, which the value for h here will be b minus a divided by 2, or you can say that h is equals to x2 minus x0 divided by 2. And very, very important is the error function, which is this one for this case, this one for the trapezoidal. The next formula is Simpson's 3/8 rule, and 3/8 is because of the 3/8 in here, but notice that here the value for n is 3, so therefore here the value for h is going to be x2 minus x0 divided by 3. Therefore, if we wanted to find the same integral by using this method now, this is what we have here. If we want to integrate from 0 to 1 of the x over 1 plus x squared, x2 here is equals to 1. So therefore the value for h will be 1 minus 0 over 3, or 1/3. So therefore it will be x0, you need to have x1, x2, and then finally x3. This obviously will be 0, this will be 1/3, 2/3, and this will be 3/3. So therefore the integral of this one will be approximately 3h, but h is 1/3 over a times f of 0 plus 3f of 1/3 plus 3f of 2/3, and then finally plus f of 1, just 1 or 3/3. So it should be just 1, which remember is 3 over 3. And then whatever that is, that's the approximation. And notice for this one, the error is smaller than this one. This one you're dividing by 90, and this one you're dividing by 80. This and this is the same, but this is bigger, so that makes the error smaller. But you had to do more computations. So therefore here, this will be 1/8. This will be 1 over 1 plus 0. And then 3, 1 over 1 plus 1/3 squared. And then 3 times 1 over 1 plus 2/3 squared. And then finally 1 over 1 plus 1 squared. Then whatever it is. All right, finally, we're going to look to the open Newton codes formulas. And here, open means you are going to evaluate the integral only at these specific points, x0 all the way to xn, where the actual interval of integration expands 1 point to the left and 1 point to the right. Okay, and in some cases, these integrals are more useful than the closed nodes, the closed Newton codes. It depends on where you're trying to integrate. And just like the closed Newton codes, here we start with n equals to 0, and the integral is just approximated by 2h times f of x0. So notice that this one is only evaluated at this point, and then this is the error term. Then if n is equals to 1, you're going to evaluate it at x equals to 0, x equals to 1, but now you go from x negative 1 to x2, and this will be the error term, and so forth. And again, the computation are straightforward. This is very simple to compute. The tricky part is going to be how do we get these formulas, or to compute the error. Well, to compute the error is not that tricky, you know the actual function. But to come out with the error formulas, it can be a little messy. But besides that, this is a straightforward. All right, so that's it for section 4.1.